Part B asks us to find the population in 1999. So for that, we're dealing with a t-value of 19 because it's 19 years after 1980. So all we need to do here is take 19 and substitute in this formula for t. We get y equals 252 times e to the 0.0095 times 19. Like I said in part A, we don't want to just use 0.0095. We want to use that whole decimal because that'll give us a more accurate solution. So if we go back, remember I stored 0.009546 and so on in for x. So when I go ahead and put this problem in, I'm going to do 252 times e to the 19x. And the calculator is going to go ahead and put this whole decimal, the whole thing, even past that, in the place of x. We should get 302.117. So let's see, we've got this is our answer here, but remember we're talking about millions of people. So we can go ahead and kind of take this decimal place and move it over. So 302 million. So our answer for this one, if we wanted to be as accurate as possible, would be 302,117,167 for rounding. Alright, so that's approximately how many people there were in 1999. Or if you wrote 302.117 million, that would work as well. But that's it for part B. Part C, when will the population first reach 400 million? So now this is a y value. So we're not plugging that in for t, but we're going to plug that in for y in part C. So we want to know when is 400 million equal to 252 times e to the 0.0095 t. So we're going to solve this kind of like we did part A. We're going to divide both sides by 252. So e to the 0.0095 t equals 400 over 252. And then we have to take the natural log of both sides. We get 0.0095 t equals natural log of 400 divided by 252. And then to find t, we're just taking this natural log divided by 0.0095, but again, use that whole decimal, so I have it stored in for x. So I'm going to do natural log of 400 divided by 252, close the parentheses, and then I'm dividing by x. So I get 48.39 or so, 48.4. So we can round that to 48 years. So that's at 48 years. Remember we started at 1980 plus 48 years later. That would be the year 2028. And now our last part here, D, how long does it take for the population to double? So for part D, we're trying to figure out when this is going to double. Well, we started with 252 million, so to double would mean that we're going to double that. So our y value would have to be 504 million, right? Because that's twice this. So we're going to go ahead and solve this. We're going to divide both sides by 252, and that shouldn't be any surprise, but when we do that, we get e to the 0.0095t equals 2, right? Because this is double that. Just like before, we're going to go ahead and take the natural log of both sides now, and we get 0.0095t equals natural log of 2, and then we just have to divide both sides by 0.0095. So we get natural log of 2 divided by x, since I stored that in there for x, we get 72.6. We'll leave it at that for right now, and we want to figure out what year that is. So again, remember we started in 1980. We're adding 72. We can round that to 73 years. So 1980 plus 73, we get 2053. So in the year 2053, that's when it would double. Or we could say 72.6 years, because it's asking how long does it take to double. We could just leave it that way.